so we have been studying. Okay, so we have been studying. So the linear algebra. Right? So the linear algebra is about vectors and matrices, right? In particular, the matrix can be written as 1n. Okay, so m. Okay, so and am1 n, right? So let me use n for here. Okay, so right? So the matrices and vectors. We've been talking about a lot of issues related to matrices and vectors, such as their operations, right? The product of matrices, etc., etc. Right? So, and in particular, very important thing we've been talking about in the last lecture is about the linearly independency and linearly dependency. Okay, so what happened here is that if you would like to solve a linear algebraic equation, let's say ax is equal to b, right? So, and what I'm going to do is that, so you can write this as a matrix vector notation, a11, a12, dot, dot, a1n, right? So a21, a22, dot, 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 a2n, right? So that give you am1, okay, so am2, dot, dot, amn, it is going to multiply the vector x1, x2, dot, 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 xn, let's say is equal to b1 up to bm, right? So that's a very typical system of linear algebraic equation. Now what I'm going to say is that I'm going to write this as a vector. So that will be a vector a1, that will be vector, this will be a vector a2. So each vector is a column vector, consists of the column here. So this will be so an, right? So there'll be n such vectors. So if you use that vector x1, x2 up to xn, let's say is equal to vector b. This is the same thing. So the same thing is from here. The ax equal to b is the same thing as saying x1, a1 plus dot 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 plus xn of an is equal to b. So that means a linear combination of these vectors a is going to give you the vector b. Okay, so that means some linear combination of the vectors a is going to give you. So that means linear combination summation I from 1 to n xi of the vector ai is equal to b. Is that good, family? Okay, so that's kind of the, in order to solve a linear algebraic equation like this, it suffices to say that a linear combination of the given vectors is going to be another given vector. Okay, so that's kind of a nice thing. Okay, so that's kind of nice thing. In particular, we see that if ax is equal to 0, has a solution, let's say has a solution x that's not equal to 0, it means that determinant of a is 0. Is a good example, right? So because if any ax equal to b, if any ax equal to b has a unique solution, determinant must be non-zero, right? So the determinant of a is just equal to 0. Okay, so somehow this kind of calls us upon this notion of linearly independency and linearly dependency. Okay, so what happened here is that let us recall the definition. Okay, so there's a definition about linearly independent solution functions. Okay, so which we have been learning. It's in the Wronskian chapter, right? So it says that if you have a family of functions fi of t, where I is running from 1 up to n, they are said to be linearly independent on an interval I if summation ki fit equals 0 implies all the ki is equal to 0. Okay, so otherwise these functions are said to be linearly dependent. So that's linearly independency. Okay, so linearly independent. It means that if summation of ki of fi of t is equal to 0, where I is equal to 1 to n, implies that each of the ki is equal to 0. That means linearly independent. Is a good example, right? So that somehow this notion can be carried two vectors also, right? So two vectors also. Let us recall that this is what we have been learning before, right? So this is what we have been learning before, is that if you have a linearly independent solution, so linearly independent functions, f1 up to fn, is the same thing as saying the Wronskian between the functions fi up to fn is non-zero, or it's the same thing as saying f1, f2 up to fn, f1 prime, f2 prime up to fn prime, dot, 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 f1 the n minus 1's derivative, f2 n minus 1's derivative, dot, 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 fn n minus 1's derivative is non-zero. So the Wronskian is non-zero. Then we say it's linearly independent. Is a good favorite, right? And this is what we have learned in our previous lectures, right? So this is what we have learned in our previous lectures, right? So now what happens to vectors, right? So what happens to vectors? Well, for the vectors, you have similar notions. Okay, so we say that the family of vectors x1 up to xn are said to be linearly independent if the summation is zero, implies all the coefficients are equal to zero. Okay, so that means we say this vectors, right? So we say the vectors x1, right? So let's say up to xn, right? So these vectors are linearly independent, right? So they are linearly independent. Right, so the vectors are linearly independent if and only if summation, let's say ai xi. So let me use ai. Okay, so let me use ai xi is equal to a zero vector, implies that each of these ai is equal to zero for I from 1 to n. Is that good, right? That's linearly independent. Okay, so that's linearly independent. Now, let me find a relation between this linear independency and the Wronskian. So what happened here is that I will rewrite this one. Okay, so I will rewrite this one as x1 up to xn. I'll treat these vectors as column vectors. Then they are multiplied by a column vector a1 up to an is equal to the vector 0, 0. So that means that if you let the matrix x to be equal to x1 up to xn, remember, these are column vectors. So that means x1 might look like x11. Okay, so x1. Okay, so let's say x1m, right? So x1m. Maybe let's say x1n. Okay, so this is a determinants. Okay, so and xn1. Okay, so up to xn, and these are the vectors. Is a good family, right? So that's instead of this solution. I mean the matrix vector equation like this, we are having something like x multiplied by a. X is a matrix, right? So the matrix x multiplied by a is kind of equal to 0. Is that good, right? So that means you see, look at the description. Description says if the summation aixi is 0, it implies ai is 0. Same thing as saying that if you have the linear equation, implies that the solution is 0 is the unique solution. Is a good fabric, right? So the 0 is a unique solution. How does you have the unique solution? Remember here, unique solution means determinant is non-zero. So here it means the determinant of the X matrix is non-zero. Just here you just have to be careful that I kind of tacitly switched the X and A, right? So that's the determinant of X is non-zero. So that means you get a relation, you get such a statement about linear independency. It says that vectors x1, right? So x1, let me say x1 up to xn, right? So the vectors x1 up to xn are linearly independent, right? So linearly independent if and only if the determinant of the column matrix is x1 up to xn. So here we are going to treat, right? So treat each of these xi as column vectors, right? So we are going to treat each of these xi's as column vectors. Okay, so we are going to treat each of these xi's as column vector, the determinant of this matrix formed by the column vectors is going to be non-zero. So linearly independent can be just checked by or justified by the determinant being non-zero condition. Okay, so determinant being non-zero condition, right? So this is kind of very nice. Okay, so here I have a nice example. Okay, so I have a nice example talking about these relations. Okay, so what does this example say? It says that if you have three vectors, x1 is 1, 2, 3, x2 is 2, 3, 1, x3 is 3, 1, 2, are they linearly independent or dependent? What should you do? Well, you get three vectors, right? So there's three vectors. X1, right? So x1 is equal to the matrix, the vector, right? So 1, 2, 3, 2, 3, 1, 3, 1, 2, right? So that's the 1, 2, 3, right? So x2 is equal to 2, 3, 1, and x3 is equal to 3, 1, 2. You want to check their linearly independent or dependent. Then what you should do is that you form this determinant matrix as I did here. So the determinant of x1, x2, and x3 is equal to the determinant of this matrix 1, 2, 3, 2, 3, 1, and 3, 1, 2, right? So you can calculate the determinant using the rule that I just I told you many times in my lectures. 1, 3, 2 is 6, 2, 1, 3 is 6, plus 3, 1, 2, 1 is 6, minus 3, 3, 3 is 27, right? So, and 2, 2, 2 is minus 8, minus 1, 1, 1 is 1. So that's 18, right? So that's, this is 18 minus 27 minus 8 minus 1. So that's kind of 10, 9 minus 27. So it's minus the 18, which is non-zero. So the Wronskian matrix is really not equal to 0, which means that they are linearly independent. Right? It's very important. If the Wronskian is non-zero, it means the matrices here are linearly independent. They are not linearly dependent anymore, right? So they are linearly independent vectors. So that's kind of one way to check these relations, right? So, and the second question is even more interesting. It says that if you have three functions, the first function is 1 plus 2t. This is coefficient is 2. 2t plus 3 over 2t squared. The second function is 2 plus 3t plus 1/2 t squared. The third function is 3 plus t squared. Are they linearly independent or dependent? What you should do? Well, you can for this kind of functionally, if you have a family of functions, you want to check they are linearly independent or dependent. What you should do is that you are going to check the Wronskian. So you calculate the Wronskian. That means remember the Wronskian, right? So that if you have the three functions, right? So if you have the three functions, f1 of t is equal to what? The f1 of t is equal to 1 plus 2t plus 3 over 2t squared. So 1 plus 2t plus 3 over 2t squared. The f2 of t is equal to this function, that's 2 plus 3t plus 1/2 t squared. So 2 plus 3t plus 1/2 t squared. And f3 of t is equal to what? It is equal to 3 plus t squared. So 3 plus t squared. Then you're going to see that the Wronskian between the functions f1, f2, and f3 are just the functions. So 1 plus, so that's let's say 1 plus 2t, right? So that is going to look like, okay, so 1 plus 2t plus 3t squared over 2. Okay, so and then it's 2 plus 3t plus t squared over 2, 3 plus t squared, right? So the first row, and you started from the second row. Okay, so starting from the second row, you're going to have their derivatives. So derivative is 2 plus, this is t squared, so 3t. Okay, so 3 plus t, and then this is 1 plus 2t, and then you take another derivative 3, right? So that's 1, that's 2. Is a good example. If you set t equal to 0 for the Wronskian, you are going to just reach the matrix 1, 2, 3, 2, 3, 1, and 3, 1, 2, which is just the matrix that you calculated here. So that's kind of non-zero. So that means that the functions are linearly independent. So this example is just trying to show you that the difference between the linearly independency of functions and the linearly independency of vectors is a good family. Okay, so this is kind of very important. You have to know what's the difference between the linearly independency of functions and the linearly independency of vectors. And another way to check linear independency is, of course, by definition. So the definition doesn't say anything about determinants, but it says something about linear combinations, right? So if you have three vectors like this, their linear combination 0, you can simply check whether or not this system of the first order linear algebraic equations has a unique solution or non-unique solution. So for example, this one, you check it has infinitely many solutions, which means you have linearly dependent solutions. Okay, so I won't talk much about this here for our future lectures. Okay, so future lectures. Now I'm going to talk about a very important kind of algebraic notion that you will use in the final. Okay, so and remember, this will be very important for your final exam. Okay, so let me say very important. Okay, so very important thing for your final exam is about so-called eigenvectors. Okay, so eigenvalues and eigenvectors. So what's eigenvalue and eigenvector? Well, these are like processed. Okay, so they are properties of matrix A. If you give me a matrix A, I can talk about the eigenvalues or eigenvectors of this matrix A. So what does it mean? Well, it means that I want to calculate the so-called eigenvalue eigenvector equation. So this equation is sometimes we call it the eigenvalue. Okay, so an eigenvector equation. Okay, so it's sometimes called eigenvalue and eigenvector equation. The word, the root eigen is probably from German. Okay, so it's not English. Okay, so the eigen, you can think of it as a principle. Okay, so you can think of eigen as principle. The eigenvalue or eigenvector can actually be regarded in English as principal values or principal vectors. So that's kind of, these are playing some important role in characterizing the matrix, right? So the matrix has such a property that has been mainly characterized by the eigenvalue or the eigenvectors. So that's what happens to this eigenvalue eigenvector equation. So if you look at this equation more carefully, what is an eigenvalue? Eigenvalue is our lambda. Okay, so eigenvalue is the lambda. Eigenvector is the x. Is a good fabric. So you can see that this is not a, first of all, it's kind of a weird equation because it has only one equation but two unknowns. If only one equation, but both the lambda and x has to be solved just from only one equation. So there's only one equation in this problem that's related to lambda and x. And moreover, okay, so if you have, so what is an eigenvector? Well, eigenvector is such a vector that if you apply this A, okay, so you apply the matrix to the vector, you're going to result just in another vector that has a collinear, right? So that means that they are aligned with the same vector. So that means you apply, you take geometrically, you imagine the following picture. You take a vector x, you apply A to it, maybe you end up with another vector A of x, which is somewhere here. But if x is an eigenvector, it means that if you start from x, you must end up with ax that's equal to lambda of x. It's kind of aligned with the vector x. Is that good, February? Okay, so that's kind of the meaning for the eigenvector. And the stretch, like the alignment, how much alignment it does, is characterized by the feature lambda that we're going to call it the eigenvalue, right? So that's the kind of the characterization of eigenvectors and eigenvalues. Okay, so now the question is, how do you solve for eigenvectors and eigenvalues, right? How do you solve for eigenvector? Now, first of all, we should observe that if an eigenvector is found, then many eigenvectors are found. Why I say this? Well, imagine that you have found an eigenvector. Let's say ax is equal to lambda x. Then it's easy to see that a multiplied by 2x is kind of 2ax this is 2 lambda x, you can treat it as lambda multiplied by 2 times x. Is a good family, right? So, but in general, a multiplied by any alpha times x will be equal to lambda multiplied by alpha times x. So if x is an eigenvector, the alpha x is also an eigenvector. So that's kind of weird, right? So it's an eigenvector, so it's not a vector at all, right? So it's a, instead of being a vector, it is actually a family of vectors that are aligned, right? So they are in the same line, but they are all called eigenvectors. Is a good family, right? So the eigenvector is actually, which we should say, an eigendirection. It is not a vector at all, but it is a direction. So we can call it the eigendirection, right? So it kind of points you somewhere to the direction. That's we call it the eigendirection. So that means when you look for eigenvectors, now somebody might get one vector, another person might get another vector. They might not have the unique solution for the eigenvector, but it doesn't matter. If these vectors are all aligned, then we are all going to call them all our eigenvectors, no matter which one you give me. Is a good family. It's not necessary on the exam, on the final exam. It's not necessary that you give me all the eigenvectors, but you can just give me one of them, and all the others are aligned with this vector. Is a good family. Okay, so that's kind of an eigenvector issue. Okay, so that's kind of eigenvector issue. But another thing you observe is that this definition is not enough, because no matter which eigenvector you take, a of 0 is always lambda equal to 0. Both are equal to 0. So that means 0 becomes an eigenvector, always an eigenvector to this equation. Then, which is kind of what we don't need this. Okay, so because this is so trivial, right? So that means we're going to put an assumption that the eigenvector cannot be 0. Okay, so an eigenvector is a vector that satisfies this relation that ax equal to lambda x, but we don't take 0 vectors as eigenvectors. Okay, so we do not accept 0 vectors as our eigenvector. So that's an eigenvector eigenvalue equation. Okay, so now comes the question. Okay, so very important for your final is that if you give me a vector, a matrix A, you should be able to find its eigenvector and eigenvalues. Now, what are we going to do that? Well, that means you must have something that satisfies the linear algebraic equation ax equal to lambda x, where x is not equal to 0. Is that good, family? How do we treat this equation? Well, the idea is the following. So you write ax equal to lambda x as a lambda multiplied by the identity matrix multiplied by x. Remember, the identity matrix is ones everywhere and 0 on the off diagonal, 1 on the diagonal. So this one can actually be further written as a minus lambda multiplied by I multiplied by x is equal to 0. So that's kind of, we can treat this matrix as a theta. So a theta of x is equal to 0 has a non-zero solution, which means what? If you have a linear system of algebraic equation that has a non-zero solution, that means the determinant of a theta is 0 or non-zero. I want to hear from you. Anybody can tell me? It's 0 or non-zero. It has, this one has a non-zero solution. Does it mean a theta determinant is 0 or non-zero? Anybody can give me idea? I want to hear from you.
0?
It's 0, right? So I like it, right? So that's because you have a non-zero solution to your linear system of equations. It means that this linear system equation has a non-unique solution. Doesn't have unique solution because x is 0 is already a solution. If you have another solution, it means at least you have 2 solutions. That means the determinant of this coefficient matrix is 0, as you said. But this coefficient matrix is nothing but a minus lambda I. So you can see that if you treat this equation, then it won't be like the eigenvalue eigenvector equation that has 2 unknowns x and lambda. There's only one unknown lambda. Is a good family, right? So this equation sometimes it is what we call the characteristic equation. Right, so this equation is sometimes what we call it the A characteristic equation. Okay, so remember we have been learning characteristic equations when we were talking about these systems. I mean, first order, higher order linear differential equation, where the characteristic equation is a polynomial equation that you just replace all the coefficients in this differential equation into the coefficients for polynomial. It is called characteristic equation. Here's another characteristic equation that's related to the algebraic linear relation ax equal to lambda x. But soon we are going to see that this characteristic equation is essentially the characteristic equation that we have learned before. Okay, so that's kind of, we're kind of, our course is like a circular, right? So we started from somewhere and we come back to this notion. So that's the characteristic. So that means the characteristic equation can give you lambda, right? So because this is just an algebraic equation, you expand the determinant, that's just an algebraic equation that can give you a lambda. Now, once you find a lambda, you have a fixed choice of lambda, let's say lambda 0. Lambda 0 is already found. So that means you just have to solve this system of algebraic equation ax is lambda 0 of x, or you can say it's a minus lambda 0 multiplied by the identity matrix of 0 is equal to 0. Either way is okay. You can solve for your x. Is a good favorite. Now remember here the x doesn't have to be unique, because if x is a solution, as we said, alpha x is also a solution. So you can just pick whatever x you like in the solution set. You don't have to worry about scaling factors multiplied by x. But usually we like to choose integers, right? For example, when we compare 1, 1, the vector 1, 1 with 1 half, both are the same. So you won't choose this one, you will choose this one because it consists of integers. Is a good favorite. Okay, so this is the way how you calculate eigenvalues and eigenvectors. Okay, so this is the way how you calculate eigenvalues and eigenvector. This is very important. Okay, so this is very important. We will be talking about it very often. Okay, so we'll be talking about it very often in our future lectures regarding systems of first order equations. Okay, so you will be using this calculation in your final exam for sure. Okay, so that's you will not it is not avoidable. Okay, so for sure you will see such problems and you will be tested your ability to solve them. Okay, to solve them. So here I give you an example. For example, can you find the eigenvalues and eigenvectors of this matrix 3 minus 1 and 4 minus 2? Okay, so that means the matrix A is a 3 minus 1, 4 minus 2. Okay, so I want to take such a matrix. Okay, so I want to calculate eigenvalues and eigenvectors. So what should I do? Well, as I said, you should start with the determinant of A minus lambda I. And what is that determinant? Well, what is A minus lambda I? A is a matrix 3 minus 1, 4 minus 2. If you minus lambda I, is lambda 0, 0. So that's the determinant. Is the determinant of this matrix 3 minus lambda minus 1 and 4 and minus 2 minus lambda. So you can get such a, so that's kind of how you raise this calculus equation. The determinant is simply calculated as lambda minus 3 multiplied by lambda plus 2. Remember here, I just flip the sign for both of this and then plus 4. So that's kind of lambda squared minus 3 lambda plus 2 lambda is minus lambda minus 6 plus 4 is minus 2. So that's minus 2, lambda minus 2, and lambda plus 1. This will equal to 0. Is a good favorite. So that means the first eigenvalue is 2, the second eigenvalue is minus 1. So it can happen, right? It can happen that you have a system of linear algebraic equation, ax equal to lambda x, you calculate eigenvalue, eigenvectors. It might happen that the eigenvalues are not unique, right? So you don't have the unique choice of eigenvalue. It might be essentially different. But for each of them, we can calculate eigenvector. How do you do that? Well, you can say the first eigenvector is ax equal to 2 of x. And if you use that definition, it means 3 minus 1, 4 minus 2 multiplied by x1, x2 is equal to 2 times x1, x2. So what do you have? Well, you have the system of equation. 3x1 minus x2 is equal to 2x1, right? So, and then it gives you the 4x1 minus 2 times x2 is equal to 2 times x2. So the first equation is actually telling you that x1 is equal to x2. Second equation is telling you that 2x1 is equal to 2x2 as we expected, because the system of linear algebraic equation is not going to have a unique solution. It will have infinitely many solutions, right? Because if each of these x is a solution, and alpha times x is also a solution, so these two equations must coincide. Otherwise, you will find a unique solution. There's something wrong. Is a good favorite. So what x do you want to take? What x do you want to take? The x here, okay, so the lambda one, so the eigenvector here, which x you want to take? Well, you can take 1, 1. Is a good favorite. Are you going to take 0, 0? Well, you're not allowed to take any 0, 0s. you must take non-zero vector. But you can take 1, 1 because x1 is equal. Of course, you can take 1/3, 1/3, but you would like to have integers for your eigenvectors. Is a good family? So you can do similar things for the lambda 2. So if ax is equal to minus of x, you get similar things 3 minus 1, 4 minus 2, multiplied by x1, x2 is equal to minus times x1 and x2. So that tells you 3x1 minus x2 is minus x1, and 4x1 minus 2x2 is minus x2. So that kind of tells you that this is the same thing as 4 times x1 is equal to x2. This one is same thing as 4x1 is equal to 2x2, so x2. So that's the two relations are the same. You can ignore the other one. And which vector you're going to take for the eigenvector? Well, you have two choices, right? So you can take x2 equal to 1, then x1 is equal to 1/4. But you don't like it because one of them is not an integer. One of the coefficients is not an integer. So you would like to have integer coefficients. So if you choose x1 equal to 1, then x2 is equal to 4. This will be good, right? These are the vectors with integer coefficients, and it's exactly what you want to have because you like integer coefficients rather than rational numbers, fractions. Is a good family. Okay, so this is how you calculate for eigenvalues and eigenvectors in practice. Okay, so this is how you calculate eigenvalues and eigenvectors in practice, and that's kind of important, especially in particular for your final exam, because we are going to ask you to calculate eigenvalues and eigenvectors for the final exam. Is that good for everybody? Okay, so that's what we want to have for the system of, the linear algebraic, algebra. Okay, so that's what we want to have for the linear algebra. So now let's come back. Okay, so let's come back to differential equations, right? So let's come back to differential equations. Okay, so we're going to kind of tell you how a differential equation, a system of first order differential equation can be solved using this linear algebra stuff. Okay, so can be solved using this linear algebra stuff. So what is our goal? Okay, so let's come back to first order systems of ODEs. Okay, so first order systems of ODEs. Right, so let's come back to the first order systems of ODE. So our goal is to solve a system of first order ordinary differential equation. And how these equations are going to look like? Well, these equations are going to have the form like x1 dot is equal to p11 of t multiplied by x1 plus p12 of t multiplied by x2 plus dot 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 plus p1n of t multiplied by xn, and you can continue doing that. Okay, so that's x2 dot is equal to p21 of t of x1 plus p22 of t of x2 plus dot 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 plus p2n of t multiplied by xn. Right, so that's kind of the system of first order ordinary differential equation, how it's going to look like. Right, so in general, you have xn dot is equal to pn1 of t of x1 plus pn2, right? So of t of x2 plus dot 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 plus pnn of t of xn. So that's the system of first order equation. But it might be possible that you have non-homogeneous term here. So g1 of t, g2 of t plus gn of t, right? So you have non-homogeneous term here. So that's kind of a complete form of a first order differential equation. But if you want to really solve it, you need initial conditions, right? So there's x1 of 0, x2 of 0 is equal to x2 of 0, dot dot dot, xn of 0 is equal to xn of 0. So you need the initial conditions for your problem, right? So you need initial conditions for your problem. Now, how are you going to solve it, right? So our goal is that you want to solve this differential equation. How are you going to solve it? Well, if you want to solve this differential equation, situation is that you would like to introduce the vector matrix notation. So you set x equal to x1, x2. Of course, these are the functions, right? So of course, these guys are functions of t. So this is x of t. And you set a matrix of t, which is p of t is p11 of t, p12 of t, right? So p12 of t and p1n of t. And dot dot dot, where you have pn1 of t, Pn2 of t dot dot and Pn of t. So you have the P of t, and then you have the G of t. Let's say is equal to G1 of t, G2 of t dot dot dot, Gn of t. Right. So therefore, this equation, this linear algebraic system of equation, can simply be written as x dot, right? So x dot is equal to P of t multiplied by x plus the G of t, where the initial value x of 0 is some x of 0 vector that's given as a confirmed. Right? So this is how you calculate, how you reduce a system of first order ordinary differential equation into algebraic this vector matrix notations, into vector matrix notations. Now it turns out that this is the crucial thing for the success of our theory. Okay, so for the success of our theory, in particular, if you have this equation like this, okay, so x dot is equal to pt multiplied by x plus, let me say, g of t, right? So that's, you have this system. Then you have two different versions of it. One is that this is what we call the non-homogeneous, right? So this is what we call the non-homogeneous equation. But it can also be like this, what we call the homogeneous equation, right? So this homogeneous equation, right? So the difference between non-homogeneous and homogeneous equation is that the non-homogeneous equation has a non-zero right-hand side, and the homogeneous equation there's only is like x dot. So this is very simple, very similar to what we have in first order equations at the very beginning of these lectures when we talk about a system of linear algebra ordinary differential equation. Then we talked about the non-homogeneous and homogeneous equation, and here is everything is the same, right? So you have a difference between the non-homogeneous and homogeneous equation. Now let me start with the homogeneous equations. Okay, so let me start with the homogeneous equation. I would like to solve a homogeneous equation. Okay, so I would like to solve a homogeneous equation that takes such a form. Okay, so that takes such a form as x prime is equal to pt of x. Okay, so x prime of the is equal to the pt of x. So how are we going to solve this homogeneous equation? Well, this method of solution is very simple. First of all, you are going to have this principle that we're going to call it the principle of superposition. So that means, so you have very simple, so you look at homogeneous equation. Okay, so let me first ask you the following question. If you, let's say when we were doing, okay, so when we were doing the system of first order equations, right? So, I mean, when we were doing the linear algebra, linear system, linear equations of higher order, right? So previous chapter, what's our root? Our root is that you first know how to solve a homogeneous equation. Once you know how to solve a homogeneous equation, you started to research on how to solve a non-homogeneous equation by putting some methods like method of undetermined coefficients and method of variational parameters. So that's what happened to the previous chapters. So now for this new chapter, like here, our root is the same. So we're going to first understand how do you solve a homogeneous equation. And once you understand how to solve a homogeneous equation, we're going to start some research on how to solve non-homogeneous equations. For the homogeneous equation, we have this very simple principle of superposition. Okay, so this is a very simple principle which we call superposition. So what's a superposition? It means that if x1, okay, so let's say x1 is a solution. So let me say x of 1 is a solution. X1 is a solution, so means x1 dot is p of t multiplied by x1. And x2 is another solution. X2 dot is equal to p of t multiplied by x2. Then if you combine these two solutions, it is easy to see that d by dt of c1x1 plus c2x2 will be equal to c1 of p of t of x1 plus c2 of p of t of x2. So that's nothing but p of t multiplied by C1x1 plus C2x2. Do you agree with me? Right, so that's kind of very simple. So it means that if these two are the solution, if you have two solutions of homogeneous equation, then C1x1 plus C2x2 is a solution. Right, so the solution set of linear homogeneous system of ordinary differential equation is a linear set in the sense that if you have two solutions, then their linear combination is also a solution. And this is exactly also the case for, remember, when we have this y of n plus a1 of t, right? So y of n minus 1 plus dot 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 plus, okay, so let's say an minus 1 of t, right? So plus dot 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 plus a1 of t, y prime plus a0 of t of y is equal to 0. Then if you have solution y1, you have solution y2, it tells us that c1y1 plus c2y2 is also a solution. Do you remember? Right? So we've been talking about the superposition principle already for just one single equation with higher order term. Now it's the same thing. So it's just the sense that situation is the same. If you have a system of homogeneous equations, linear system of algebra, system of homogeneous equation, that if you have two solutions, you superposition them, you're going to get another solution. So the solution set for the system of ordinary differential equation is a linear set, right? So it's a linear set. So then we're going to talk about the Wronskian of these solution functions, right? So this is exactly the idea that we have been talking about in the previous lectures, right? So you can see that this lecture is very similar to this part where we talked about before. What you're going to do is that you first obtain a family of solutions. Then you're going to check if their fundamental solution, W of y1 up to yn, is y1 up to yn, y1 prime up to yn prime, dot dot dot, and y1 n minus 1's derivative up to yn n minus 1's derivative. You're going to check is 0 or non-zero. Is a good fabric, right? So this is what we have been learning this in our previous lectures. Now we're facing the same thing, right? So now we're facing the same thing. So that means you are going to have a system of algebraic linear. This system of equation x dot is equal to p of t of x. For example, suppose you get a family of solutions x1 up to xn. So that's kind of the case. If P of t is an n by n matrix, then you must get n linearly independent solutions. Is a good fabric, right? So you must get n linearly independent solution. Then we have this notion for general solution. If you want a general solution, then it must be x of t is c1x1 of t plus dot 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 plus cnxn of t, just as we did before. Is a good fabric. Now, how do you check that this c1 and cn is going to exist? Well, you're going to see that these solutions are going to be linearly independent. Right? So you're going to check these solutions are linearly independent. How do you check they're linearly independent? Well, x1 of t, right? So x2 of t, these are functions of t, right? So xn of t are linearly independent. Right? So are linearly independent. You're going to check this if and only if you put the w of x1 up to xn. This is the Wronskian for a family of vectors. So what you would like to do is just to check x1 of t up to xn of t. You treat each of this vector as a column vector. Right? So you treat each of this vector as a column vector. You put them in a row. You're going to get a square matrix. If this is not equal to 0, it means your solution are linearly independent. Is a good fabric. If they're linearly dependent, this is going to be equal to 0. Is a good fabric. So this is kind of the idea. Okay, so but remember, for the Wronskian here, you have to take derivatives. For the Wronskian that I discussed here, you just only have to put all these column vectors in a row. And this is exactly what we have been talking before, right? So at the very beginning of today's lecture, we were talking about this. If you have a family of vectors, they are linearly independent. You check the Wronskian, you just put these vectors in a row. But if you have functions, then you have to take derivatives of those functions in order to form the Wronskian matrix. So that's the difference between a vector Wronskian and the function Wronskian. Is a good value. Okay, so that's kind of course upon this notion for linear independency. If the Wronskian of n vector functions is just defined by taking a determinant of putting all these vector functions as column vectors in a row, and you calculate the determinant, that's the Wronskian. Okay, so that's the Wronskian. Okay, so you have this Wronskian. Now we have another theorem. Okay, so the theorem says that if the vectors functions x1 up to xn of t, they are linearly independent, then the Wronskian is non-zero. Conversely, if the Wronskian is non-zero, the vector functions are linearly independent. We've been talking about this before, right? So we've been talking about this before. Okay, so maybe that's all I would like to say for today's lecture. Okay, so that's maybe